In this tutorial, we will show how to implement battery storage for the peak shaving strategy in simulations of grid-connected systems. Many grid-connected PV systems today are equipped with a battery energy storage system, or short BESS. The purpose of such hybrid systems can differ from case to case. In this tutorial, we will describe the so-called peak shaving strategy, which aims at recovering curtailed PV generation. If the grid operator limits the power that can be injected into the grid, a BESS can store energy during periods of overproduction and release it at a time when the PV generation drops below the injection limit. This will have two advantages. On one hand, the PV plant owner can recover benefits which would otherwise be lost. On the other hand, the grid operator has a simple way to regulate the renewable energy generation. Therefore, for this kind of system, we need to add a battery to the PV system and specify its charging and discharging behavior according to the PV generation and the injection limit. In this tutorial, we will go through an example of a PVsyst simulation with a peak shaving strategy. To start, please open the project Demo Residential System at Geneva and select the variant VC0. Now click on Storage. This will bring up an empty window with a single selection box. From the drop-down list, you first have to choose a storage strategy. For this tutorial, we will choose Peak Shaving. This will bring up two tabs, out of which the second one, called Peak Shaving, is pre-selected. On the top right message box, a message is displayed asking you to define the grid limitation value. For our example, enter 5 kW in the field grid power limit. Next, in discharging, you have to define when the battery starts injecting to the grid. You can choose out of 4 different options. The first option, which is also the default, is as soon as power is needed. With this option selected, the battery will start injecting energy to the grid as soon as the generated AC power is less than the grid power limit. The second option is after sunset. Here, the grid injection only starts when the PV generation has dropped to zero at the end of the day. The third option is from a specified hour. If you select this option, a field will appear allowing you to input an hour of the day. Injection from the battery to the grid will only happen from that hour onwards. The fourth and last option is during a specified hourly period. With this option, 2 fields will appear, allowing you to input specific hours of the day. The battery discharging will only be possible between these 2 values. For this tutorial, leave the parameter on as soon as power is needed. At this point, you cannot define the maximum charging power and the maximum discharging power because the storage pack is not yet defined as indicated by the message in red. We will do this in the next step. For this, we now select the tab Storage Pack. This tab allows us to define the type and number of batteries for the BESS. In the selection field for the manufacturer, we keep the choice Generic, and in the drop-down list on the right, we select the first option, Battery Module Lithium-Ion 25.6 volt and 180 ampere hours. This is a module made out of 58 stacks of 8 lithium-ion cells each, giving a total of 464 individual battery cells. As soon as we have chosen the battery pack, PVsyst pre-fills the fields Modules in Series and Modules in Parallel. In our case, a single module in series has been chosen, and 7 batteries were put in parallel. The resulting number of modules is 7, giving a total number of elements or cells of 3,248. This configuration was created automatically by taking into account the daily curtailed energy that cannot be directly injected due to the network limitation. On the right side of the battery configuration, you can see several figures that summarize the properties of the battery pack. You will notice that the battery pack voltage is rounded to an integer value, 26 volts in our case. The C10 rating is the capacity of the battery if it discharges completely over a period of 10 hours. The battery pack in our example has a global capacity of 1260 ampere hours. For the stored energy at 80% depth of discharge, short DOD, we get a value of 25.8 kilowatt hour. This value is indicative for the energy that is stored in a single battery cycle. For lithium-ion batteries, the charging cycle should never be 100% DOD, since a deep discharge or an overcharge reduces the battery lifetime or can even cause irreversible damage. The total weight is also displayed for information, to give a rough idea of the physical size of the battery. The next line shows the number of cycles that can be performed at 50% depth of discharge before the battery reaches the end of its life. And finally, you can read off the total energy that can be stored over the battery lifetime, which in our case is almost 50 megawatt hours. In the bottom left box, you can choose the battery operating temperature that will be used in the simulation. The battery temperature is used in the aging model of the battery. An increase of 10 degrees Celsius in the operating temperature reduces the static battery life by a factor of 2. Now that the battery pack has been defined, we have a message in red at the top right telling us to define the maximum charging power of the battery pack. For this, we have to come back to the tab Peak Shaving. To get the default value for the maximal discharging power, we click on the checkbox next to it. The charging power should be able to cover the PV generation peak minus the grid injection limitation. The default value is obtained from the maximum output power calculated by the Clear Sky model, from which the grid power limit is subtracted. In our example, this gives a value of 3.2 kilowatt. Decreasing this value may lead to energy losses for the hours when the PV generation is at its maximum. Increasing this value will not get any benefit, since these levels of charging power can never be reached. However, the maximum charging power will impact also the lifetime of the battery. Please refer to the datasheet to make sure that the chosen charge and discharge power will not damage the battery. In our example, we will leave this value at its default, which is 3.2 kilowatt. Again, click on the checkbox next to the value in order to get the default value calculated by PVsyst, which is 6.2 kilowatt in our example. This value is too high since the grid limitation requires never to exceed 5 kilowatt. We therefore set this value manually to 5 kilowatt. In the box Battery SOC Threshold, where SOC means state of charge, we can define the maximum charging and minimum discharging levels. By default, PVsyst set up these values so that charging stops when the battery is 95% full, and discharging will stop when a SOC of 20% is reached. As mentioned before, with lithium-ion batteries, deep discharge and overcharging should be avoided to ensure a long battery lifetime. For our example, we will leave these values at their defaults. All the other fields in this dialog also contain already reasonable default values. We can leave them at their current values and click on OK. The peak shaving scenario is now configured and we can run the simulation. Once the simulation has finished, we can have a first look at the system performance by clicking on Loss Diagram. You can see on the lower part of the diagram that the energy flux is divided in two. There is the direct energy used when the PV generation is directly injected into the grid, and there is the stored energy which corresponds to the energy that is first stored in the batteries and then injected into the grid at a later time. With the peak shaving strategy, you can recover energy that gets curtailed at times of high PV generation.